that's going to be root of pi squared minus 8 divided by 4 pi squared. This one I can also take it out. It's going to be equal to Vd divided by 2 pi multiplied by, root of p squared minus 8. Let me double check again. See if I made any mistakes here. I don't have my calculation. I didn't calculate this one, but I feel like it's okay. Let's double check everything. Vd squared over 4 minus 2 Vd squared over pi squared. Vd comes out, pi squared minus 8 divided by 4 times pi squared becomes V sub d divided by 2 pi root of pi squared minus 8. Okay, looks okay. So let's just like see why we calculated this one. So our DC to AC converter or inverter created this signal for us. This is not what we wanted. This is what we wanted, right? But the signal that got created, it has some harmonics, which we have its RMS value. Okay, so now we can calculate the total harmonic distortion of this signal. And if you remember from when we discussed rectifiers, the total harmonic distortion is basically the undesired components over desired components, right? In this case, what is desired? This one. What is not desired is this one, right? So let's find the ratio of these two. It's going to be Vd over 2 pi root pi squared minus 8 divided by root 2 divided by pi times Vd. Vd's cancel out, pi cancel out, so it becomes root of pi squared minus 8. 2 root 2, if I take it inside, becomes 8. So it's basically, it's this pi squared divided by 8 minus 1. Okay. You can calculate this value. I did it before. It's somewhere here. Yeah, so it should be about 48% if I haven't made any mistakes. Okay, so the THD, the total harmonic distortion for a half wave inverter, is about 48%. It means that the ratio between undesired to desired components is 48%. Okay, so it means that if, like, let's say, like if we consider this 100, then we have 50% stuff that we don't need, but we have them, right? And the half wave inverter gives us some harmonics. This is an indication of how good or how bad an inverter is or a rectifier is. THD is something that you use to compare different inverters or different rectifiers. And this tells us that this inverter has 48% THD. Okay, how did we calculate this? We calculated the RMS value of the signal. We calculated the RMS value of the fundamental frequency. From that, we found the harmonics RMS value, right? This harmonic RMS value, it basically has the DC component, which in this case was 0, plus all the higher order harmonics. So B2, B3, B4, B5, B6, and so on. So all of them, if you add them up, it's going to be like this, right? I didn't want to calculate all of them and find the summation, B2 and B3 and B4 and so on. So I use this formula that tells us that VRMS is equal to basically V1 squared plus V harmonic squared. Okay. Previously, like for rectifier, we used the same formula, but we said like VDC squared plus VAC squared, because in rectifier this was our desired, and this one was all the sine forms, like all of the A1s, B1s, A2, B2, A3, B3, and this is what we use. But here, because I want to know like what V1 is, I'm using this formula. Okay, so just keep this number in mind. And so we are done with the half wave inverter. Now we're gonna go to full wave inverter. So we're gonna do exactly the same thing that we did here for full wave inverter. I don't expect you to do these calculations in the exam, but I want you to understand what's happening here. Like what THD is, what the fundamental frequency is, and why we use Fourier transform, right? So this is something that I expect you to know, but the calculations, don't worry too much about them. So for the full wave inverter, the signal that was created was something like this. And then it continues. This is T, this is T over 2, this is T over 4, this is 3T over 4, and so on. Okay, one thing I should mention, this part that the signal is 0, it's not necessarily the same period as this one, right? That depends on the modulation you use, right? So this can be bigger than this one. Right now, I'm just using a very simple circuit, assuming that the time that the signal is 0, it's the same as this one, right? So that's what we are using, but based on the modulation technique you use, this can be smaller or like even bigger. So now for the full wave inverter, as you can see, the DC component is again 0. This is VD, this is negative VD. Let's first calculate the RMS value of the signal itself. So V of R